So let's start with this paper, which is Summer 23 paper 42. Let's get right into it. Another homework paper. A student measures the capacity of a drinks cup by 3 different methods. The capacity of a cup is the max volume of liquid that it can hold. Method 1, the student measures the height h of the cup, diameter d, and diameter small d of the bottom of the cup. So this is also shown here. Measure the height, the diameter, and the small diameter, small d, of the cup in the diagram. So these values you just need to measure and write down. But do keep in mind that you'll be measuring this with a scale or a rule which also has a precision of 0.1 centimeters. So even if you do get exact values, write it correct to 0.1 centimeters. So these should be 8.3, 6.9, and 4.6 centimeters for each of these dimensions. Calculate the average diameter dA of the cup using your readings from A1 and the equation which is shown here. So we just add both of these, divide by 2. So 6.9 plus 4.6 over 2. Right? So this turns out to be 5.75. But remember that if I were to, for example, plot this in a table, I would also give this correct to 5.8 because the above values are also one decimal place. This should also be the same. Next, we calculate a value for the capacity, the volume basically using these values. So pi times the square of this times h, the height 8.3 over 4. So this value turns out to be, so exactly this is 215.5, or we can say 220 correct to 2SF. Right, or you can also say 216 to 3SF. Next part, the student uses a length of string and a meter rule to determine the average circumference C of the cup. Wrap some of the string 5 times around, that is 87.9. So one circumference is going to be 87.9 over 5. It turns out to be 17.58 or 17.6. Using values of h from A1 and C from B1, calculate a value for the capacity using this equation. So C square, so 17.6 squared times h, which was 8.3, divided by 4 pi. This turns out to be 204.5. So you can say this is 205 or 210. Both make sense. So this is what this value turns out to be. Method 3, the student fills a measuring cylinder with water up to the 220 cm cube mark, pours water from the measuring cylinder into the cup until the cup is full, records a new reading R on the measuring cylinder. Write down the new reading R, which is shown in this figure. So this should be 30, right between 20 and 40, and this should be 32 cm cube. Right? Determine the volume of water V3 in the cup showing your working. So 32 is the new value, right? And first it was filled up to 220, and then you pour water from the measuring cylinder until the cup is full. So 220 cm cube was what it was already filled with, and after pouring you're left with 32. So 222 minus 32 is what we're looking for here, which is 188 cm cube. Next part, all 3 methods of determining the capacity of the drinks cup gave values which are approximate. State one reason why the volume calculated in 2 and one reason why the volume calculated in 3 are not accurate. So for 3, I just saw that it would be pouring the liquid, right? So I can talk about some splashing or some water being spilled, right? So water spilled or splashing on transfer. This is like one of the most obvious ones. Then you could have also written something like parallax error. That would also work in this case. And what was method 2? Method 2 was the string, right? So when you wrap the string around and then you, what do you call it? And then you measure the circumference. So it may also be the case that if, for example, if you're wrapping string around, let's say if you're wrapping string around a container that's like this. Now ideally you know that how you should wrap around is all of these loops must be closely positioned to one another. And similarly, you could have also left some spaces between them, right? And you could have also overlapped the string, which is also not going to be the correct value of the circumference. So I can say this, that the string, so the string loops may have overlapped, or there could have been spaces between them. All right. Again, so yes, overlapping can create a change in the circumference, but having spaces would not, right? Because we are measuring how many turns it goes around. So yeah, let me correct myself. Spacing would not have a change on the circumference, but overlapping would. All right. Question number 2. A student investigates the effective resistance of different combinations of resistors and lamps in circuits. So the student sets up the circuit shown. So you have the ammeter here, which basically measures the current which is coming out of the power supply. You have these two in series, this one in parallel with these, and you are measuring the voltage across this connection, right? Which is also the voltage which is really supplied by the power supply. The student closes the switch, measures the potential difference V1 across the resistors and the current I2 in the circuit, opens the switch, then again. Readings are shown. So this must be the voltmeter reading, which is 2.9 volts, and this is 0.45, and then after that it's another division, so 0.46 amperes and 2.9 volts. 2.9 volts and 0.46 amperes, right? Now let's go on. Calculate the effective resistance of the combination of the resistors using this equation V1 over I1. So 2.9 over 0.46 turns out to be 6.304347. So we can give this as 6.3, or you can also give it to one more SF, because these two are 2 SF each. Suggest why switch is opened after the readings of potential difference and current are taken. We've talked about this time and again. So this is to prevent the wires or the components overheating. And in a way, this also basically extends the life of the battery, because it can then run for longer in more circuits. Student rearranges the circuit, so now the resistors are connected in parallel as is shown. Now he takes the new readings, 2.8, 0.88. Record your answer on the second line. So calculate the effective resistance, that's R2, and then also write down the value of 2 R2. So 2.8 over 0.88 is 3.1818, so 3.2 amperes, right? If you're again keeping this 2SF, and then the double of that is going to be 6.4 ohms. If the two resistors are identical, theory suggests that R1 equals to R2. Two quantities can again be considered to be equal if they are within 10% of each other. State whether the results indicate that the resistors are identical. Support your statement with a calculation. So R1 was 6.3 and 2R2 is 6.4. So you have 6.3 and 6.4. Now again we do 10% of 6.3, which is 0.63. So 6.3 plus 0.63 is a value which is 6.99, right? So let me do this, 6.99, and 6.4 does lie within this range, so yes, since they are within 10%, right? So yes, equal, since they are within 10%. Let's go on. The student repeats the experiment in A and B but replaces the resistors with lamp. He obtains the following results. Effective resistance R3 of the combination of lamps is 5.2. R4 of the connection of lamps is shown in 2.4. So 2.1 and 2.4. So this is 2.5. This is 2.4. Right? So all three in parallel, that is 2.4. And then like this is the other reading, right? So 2 in series and another one in parallel is figure 2.1, and all the three in parallel is 2.4. The teacher explains that the resistance of the filament lamps changes due to a heating effect, and therefore R3 is not equal to 2R4. Suggests one observation that the student makes while doing the experiment that supports the teacher's explanations. So what would happen if the resistances are changing? So when doing this, he can obviously see that the resistances would change, so the meter readings can also change, right? So the meter readings can change, and also because of the resistance, you can also say that the brightness of the lamps change, right? So brightness can change. And you can also say meter readings are changing. Could be any of these. Part E, student extends the investigation using a different combination of the three lamps to the two combinations already used in A and B. Complete this circuit diagram to show a third way of connecting the three lamps. So there could be two ways, right, if you know about this. So we've done 3 in parallel, 2 in series parallel to another one which is alone. You can do 2 in parallel and 1 in series like this. This is also not covered in the arrangements above. Or an easier one could have been if you had all the 3 in series, right? That also works, this also works. Question number 3, a student investigates the image formed by a converging lens. Student arranges the apparatus as is shown, measure and record this height h. So h turns out to be, again, you measure this with your scales. So this turns out to be 2.7 centimeters. Next, the student switches on the lamp and places the lens a distance of 20 centimeters from the triangular object. Adjust the position of the screen until a sharp focused image of the triangular object is formed on the screen. So this here is the triangular object, right? So, alright, so this is done. The image is shown full size here. Measure the height h of the image. So the height h turns out to be 7.8 centimeters. Did I write the units above? So it was given. So this is 7.8 centimeters. It's a full size image, so no scale to be used here. Calculate the value of 1 over h, give your answer to 2SF. So 1 over 7.8 turns out to be 0.13 to 2SF. Add your values for h and 1 over h in the table. So 1 over h, and I also need to complete the column heading, so this should be 1 over centimeters, right? And h is just in centimeters. So h was 7.8 and the corresponding 1 over h is 0.13. Student repeats B for all different values of u. He records all his readings in 3.1. So we've completed the headers. Calculate the remaining values of 1 over h. Needless to say, this is also going to be to 2SF. 1 over 3.9 is 0.256, so 0.26. 1 over 2.6 is 0.384, so 0.38. 1 over 1.6, 0.625, so 0.63. And 1 over 1.1, 0.909, so 0.91. The screen is a square sheet of white card of side 10 cm. Look at the data in table 3.1 and suggest why the screen does not use values of u which are less than 20 cm. So what was u even? U was this distance, right? So this is 20 cm. The least value is 20 cm. They want us to explain why do we not use values less than 20 cm given the dimensions of the screen, right? So if we had 20 cm, the height of the image was 7.8. So if I use a value smaller than this, you can see that this value would be larger, right? You can see that as u is increasing, h is decreasing from here to here and vice versa. So smaller u would lead to a larger h, which could not be captured on the screen. So then I would say the image is too big for the screen. On the grid provided, plot a graph of 1 over h on the y-axis against u on the x-axis. So this is what we now need to do. Start both axes from origin 0, 0. Again, let's take the values with us. So that's what we have. Let's keep it here. So again, 1 over h is on the y and u is on the x. So for u, if we want to figure out a scale, we want to go up to 50. So how about 10, 20, 30, 40, 50, right? This is the best we can do. So this is u, which is in, what's the unit? U is in centimeters. So 10, 20, 30, 40, and 50 here. And then similarly for the other ones, which are 1 over h on the y-axis. So 1 over h units are in 1 over centimeters as well. So this goes up till 0.91, right? So how about 0.2, 0.4, 0.6, 0.8, and 1? All right. So 0.2, 0.4, 0.6, 0.8, and this is 1.0. Now we start plotting. So at u20, 1 over h is 0.13. 0.13. So this would be 0.1, 0.12, and 0.13 would be in the middle. So again, let's place a small dot here, right? Then I have at 25 I have 0.26. So u is 25, 1 over h is 0.26. So 25 would be right in the middle, and 0.26. So 0.22, 24, and 0.26. Let's do this again, right? Then u30 is 0.38. So 30 and 0.38 is just going to be one box of the 0.4. Right? The smaller are these dots that you place, the easier is going to be the construction of the line. And then you have 40 and 0.63. So 40 and 0.63. All right. And 50 and 0.91. 50 and 0.91. So 0.9 and 0.91. So we have to do a line, right? Even though this for some reason looks like a curve. Oh, I made the first one wrong. That's why it looks like a curve. This one is at 20, not at 10. So 20 comma 0.13, 0.1, 0.12, and 0.13. Right? So now it looks like a line again. So I have these 1, 2, 3, 4, and 5 points. Again, let's lay out the line. So this looks pretty nice, right? Leaves out this here, leaves out this here, slightly above the line. Alright, calculate the gradient of the lines, show all your working and indicate what graph values you use. So one of these, let's take it to be this point right here, which looks like what? So it's not quite 15, it's more like 15 and a half. So this point is 15 and a half comma 0. Another point, let's take this one closer to the top. So it does seem to be going through this point right here, which is 0.9 and 0.92. So this is 0.91 comma 50. Actually, this now coincidentally happens to be one of those points which was also part of a table. But you shouldn't let your choice of points be biased because of the points you plotted. Right now, this is just a coincidence which just happened. So gradient change in y over change in x. So 0.91 minus 0 over 50 minus 15.5. So let's see what this turns out to be. 0.91 over 50 minus 15.5. So 0.02637. So 0.02637. They don't give me any significant figures, a choice on the significant figures. This is 2SF, so I can give it to 2SF again or to 3SF. So 0.026 is what I get. Calculate the focal length, use this value of h and the gradient. So f equals 1 over 0.026 and capital H, which was what? 2.7 times 2.7. So this thing times 2.7, 0.026 times 2.7 to the negative 1, 14.24, so 14 cm, right? When measuring the height of the image on the screen, the student's hand and the ruler obstruct the light from the object and prevent it from reaching the screen. Suggest one improvement to the apparatus used by the student to overcome this problem. All right. So the measurement of this height, this was a problem, right? Because there's the light which is also coming in. So you can clamp a ruler to the side and then you can read off here, right? So this is an easy one. Another one which is also commonly used is if you use a graph paper on the screen, or if you have some sort of a scale on the screen, that also makes it easier. So either of those work. Question number 4, our planning question. A student investigates the time taken for ice cubes to melt when they are placed in a beaker of hot water. Plan an experiment to investigate how the thickness of the cardboard insulation around a beaker affects the time taken for the ice cubes to melt. Following apparatus is given. In your plan, you should explain briefly how to do this. Again, the same thing every time. So we have to do the thickness and how it affects the time taken for the ice cubes to melt. So right now I know that what my independent and dependent variables are. So I'll be varying the thickness of the insulation. So vary thickness of insulation and measure time taken for stopwatch to melt, for the ice to melt. And then we can also say that that time is to be taken using a stopwatch, right? So explain briefly how to carry out the investigation. So how do we do this? Now this is pretty easy. that you have this 250 cm cube beaker, supply of hot water, supply of ice cubes, thermometer, stopwatch, supply of 2 mm thick cardboard sheets, right? So obviously I'll use the beaker, and in this beaker I'll pour the hot water, I'll place the ice cubes, and then the thermometer will tell me how much the temperature is dropping by. Stopwatch is for taking the time, and then I can cut out some portions of these to create varying thicknesses, right? So first things first, I defined how to do this. Then I'll say that pour the water in the beaker. Let's actually do this here. So pour known volume. Also, it actually does also ask me for the control variables, right? Let's first do that and then do this. So for the control variables, what should be kept constant? These are also very, very obvious, that the hot water must always be at the same temperature. The amount of hot water must also always be the same. You can say the room temperature should be the same. Temperature of ice cubes could be the same. You can talk about a lot of this. So mass of water, so mass and temperature of hot water must be constant. So then something about the experimental method. So pour known volume of water into beaker, and then drop the ice cubes in. Ice cubes. And then about the varying amount of insulation, so we can say that cut through the layers to create, now again, at least 6 different thicknesses of insulation, and then wrap around the beaker and measure the time. So was it the time for the ice cubes to melt or what? And measure the time, yeah, so for the ice cubes to melt. Measure time for melting using a stopwatch. Right, so that's a lot about the experimental procedure as well. What else do we have? Draw a table with column headings to show how to display the readings, right? So table, again, let's make the table here. So for the table, what are you varying? That's the entries you'll have here. I don't think we'll be needing this one. Again, not required, but still, serial number. This one would be thickness of the material, and this would be, for example, in centimeters, and this is the time, which could be in seconds, right? Again, reaching a conclusion, just plot a graph of thickness versus time. Versus time to obtain conclusions about their relationship. That's the planning question, and the paper also concludes. So see you in the next live session then.